Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the CPLD and we will see the typical architecture of the CPLD. So the CPLD stands for the Complex Programmable Logic Devices. So in the previous videos, we have already seen the different types of programmable logic devices like the PROM, PLA and the PAL. So all these programmable logic devices are known as the SPLD, where this SPLD stands for the Simple Programmable Logic Devices. And using these SPLDs, it is possible to implement the simple logic circuits which does not require much product terms as well as the outputs. For example, in the last video, we have already seen the PLIC, which is known as the 22V10. So as you can see, it consists of the 10 outputs and each output of the OR gate consists of 8 to 16 product terms. But if you want to design a much complex circuit, then we may require more outputs as well as the more product terms. So for a complex circuits, instead of increasing the outputs as well as the product terms in the each OR gate, multiple such SPLDs are combined in the single chip. And such programmable logic devices are known as the CPLD, that is the Complex Programmable Logic Devices. So if you see any CPLD, then it consists of multiple SPLD-like blocks, and these blocks are connected with each other using the switch matrix. So sometimes this switch matrix is also known as the Programmable Interconnect Array. And as you can see, each such SPLD blocks is connected with the IO block, where this IO block consists of the input-output pins as well as the input-output buffer. So using this switch matrix, it is possible to connect the output of one SPLD to the input of another SPLD block. For example, using the switch matrix, it is possible to connect the output of this SPLD as an input to the another SPLD block. So these SPLD-like blocks in the CPLD are known as the logical array block. So the different manufacturers refers this block with the different names. So sometimes it is also referred as the configurable logic block. So in this video, we will refer it with the logical array block, and during our discussion, we will see the architecture of some commercially available CPLDs. And moreover, we will also understand the internal logic of each block. So from vendor to vendor, you might see some changes in the CPLD configuration. But more or less, if you see the overall architecture of the CPLD, then it will remain same. So this is the architecture of the Altera Max 7000 series CPLD. So as you can see, it consists of 4 to 16 logical array blocks, and each block is connected with each other using this programmable interconnect array. Moreover, if you see this each logical array block, then they are also connected with the input-output block. So depending on the exact model number, the number of logic array blocks in the CPLD may change. Now if you see the each logical array block, then it consists of several macrocells. So if you see the each macrocell, then it consists of several AND gates and the OR gates. And apart from that, it also consists of the flip-flops and the several other configurable options for the output. So during the video, we will see the internals of this macrocell in detail. But the point is, here the each logical array block consists of several macrocells. So in this case, as you can see, it consists of total 16 macrocells. So from the each logical array block, total 16 outputs are going to the switch matrix. That means if required, then with the help of the switch matrix, the other logical array blocks can use these outputs as an input. And the same 16 outputs of the macrocell can also be used as an output of the CPLD. That means the same 16 outputs are also going towards the IO block. So depending on our requirement, it is possible to configure these outputs. So here, all these IO pins can also be used as an input. So here, from the each IO block, 16 inputs are going towards the switch matrix. And through the switch matrix or through this programmable interconnect array, all these different logical array blocks can access these inputs. So as you can see, from the programmable interconnect array or from the switch matrix, total 36 inputs are going to the each logical array block. So this is the overall architecture of the CPLD, which is manufactured by the Altera. But if you see the CPLD architecture of the other manufacturers, then more or less it will remain the same. For example, This is the architecture of the XC9500 CPLD, which is manufactured by the Xilinx. So of course, depending on the manufacturer, the nomenclature will be slightly different. For example, here the programmable interconnect array is called the switch matrix, while if you see the logical array block, then here it is known as the functional block. Moreover, here the number of macro cells in the each block is also different. But if you see the overall architecture of the CPLD, then more or less it will remain the same. So now let us briefly see what is inside the each block of the CPLD. And first, let us see the internal structure of this Macrocell. So this is the internal structure of the Macrocell of Altera Max 7000 CPLD. So as you can see, this Macrocell consists of total 5 AND gates, and using these, it is possible to generate the 5 product terms. Then after, there is a product term allocator, which is also known as the product term selection matrix. And this block decides which product terms will get connected with the OR gate. So apart from its own product terms, here it is also possible to use the unused product terms from the other macro cells. So in the Altera Max CPLDs, to use such unused product terms, we have two options. So these two options are the shared logic expander and the parallel logic expander. That means using these options, it is possible to expand the number of product terms in the macro cell. Then after, we also have the OR gate and the XOR gate. So using this OR gate, it is possible to add all these product terms, and it is possible to generate the output function in the sum of product form. And using this XOR gate, if required, then it is possible to invert the output. So basically, if we want the output in the product of sum form, then it is possible to generate it with the help of this XOR gate. And if required, then it is also possible to perform the XOR operation on the different product terms. So apart from that, the Macrocell also consists of the flip-flop. And with the help of the flip-flop, it is possible to store the output of this OR gate. So here, it is possible to configure this flip-flop as either D flip-flop or the T flip-flop. So apart from that, here with the help of the multiplexers, here it is possible to configure the output as either registered output or the combinational output. That means here, with the help of the multiplexer, it is possible to bypass the output of this flip-flop, and it is possible to connect the output of the OR gate to the output pin. So as you can see over here, this output of the multiplexer is going towards the IO block, and the same output is also going towards the switch matrix. So that is the basic block diagram of the Macrocell. So now let us see what is the shared expander in the Macrocell, and using that, how is it possible to expand the number of product terms in the Macrocell. So this specific feature is only available in the Altera CPLDs. So as per this feature, if required, then each logical array block can have additional 16 product terms. So we have seen that each Macrocell can generate total 5 product terms. Now out of these 5 product terms, if the Macrocell has some unused product terms, then out of these unused product terms, each Macrocell can share one of the uncommitted product terms with the other Macrocells. So of course, here this sharing of the product term is happening within the same logical array block. That means within the same logical array block, each Macrocell can share one of the uncommitted product terms with the other Macrocells. So this one such uncommitted product term which is shared by the Macrocell with the other Macrocell is known as the shared expander. So in the specific logical array block, if all the 16 Macrocells share one such unused product term, then in that logical array block, we will also have the additional 16 expander terms. So as per the requirement, all the Macrocells in the logical array block can use these shared expander terms. So as you can see, first this product term is inverted, and then it will be shared with the other Macrocells in the particular logic array block. So in the Altera Max CPLD, since each logical array block has total 16 Macrocells, so if all the Macrocells share one such expander term, then we will have at the most additional 16 product terms. And by using this additional shared product terms, the Macrocell can expand its total number of product terms. So as we have seen, by default, each Macrocell has total 5 AND gates, and that's why it can generate total 5 product terms. But by using these shared product terms, it is possible to increase the number of product terms at the output of this OR gate. So let us see that. So let's say in a CPLD, these two are the Macrocells of one logical array block. So here let's assume that in one of the Macrocell, this last product term is unutilized. And that's why this product term is used as a shared expander. So as you can see, here this D bar and the E bar inputs are connected with this product term. That means the output of this AND gate will be equal to D bar dot E bar. And after the inversion through the NOT gate, the output will be equal to D plus E. So now this product term will be shared with the other macro cells. So here let's assume that the neighboring macro cell is using this shared product term. So without this shared product term, if you see the output, then that is equal to A bar dot B bar plus AB plus A bar dot C bar plus BC plus B bar dot C bar. But here, since the shared product term is used with the last AND gate, so the overall output will be equal to A bar dot B bar plus AB plus A bar dot C bar plus BC plus this B bar dot C bar dot D plus E. So the overall output will look like this. And after the further expanding, we will have total 6 product terms. So as you can see, by default in the macro cell, we can generate at the most 5 product terms. But using this shared expander, it is possible to generate more than 5 product terms. So in this way, using this shared expander, it is possible to increase the total number of product terms in the output. So like I said earlier, this shared expander feature is only specific to the Altera CPLD. But if you see all the CPLDs, then they have a feature that is similar to the parallel expander. So as per this feature, in the given logical array block, if one macro cell has some unused product terms, then it can be shared with the other macro cell. So we have seen that in case of the shared expander, each macro cell can share only one product term. But here in the parallel expander feature, if required, then the macro cell can share more than one product terms. So this product term allocator or the product term selection matrix will allocate this additional product terms to the required macro cell. So as you can see over here, the 5 product terms from the upper and the lower macro cells are shared with the central macro cell. That means the macro cell in the center has total 15 product terms. Now here, it is not always necessary that the macro cell should share all the product terms. That means if some of the product terms are being used by the macro cell, then it can share only the unused product terms. For example, here in the first macro cell, these 2 product terms are being used by the macro cell itself. So here, the remaining 3 unused product terms are shared with the lower macro cell. So along with the 3 product terms that is being shared by the first macro cell and its own 5 product terms, the second macro cell is sharing total 8 product terms with the third macro cell. And here, this fourth macro cell is also sharing its 5 product terms with the third macro cell. That means here, total 13 product terms are being shared with the third macro cell. And along with its own 5 product terms, this third macro cell has now total 18 product terms. So in this way, the product term allocator or the product term selection matrix shares the unused product terms with the other macro cells. So that is basically a parallel expander feature in the CPLD macro cell. And using this, it is possible to increase the number of product terms in the macro cell. So all this product term sharing is happening through the product term allocator or the product term selection matrix. And this is the internal logic of the product term allocator. So as you can see over here, these 5 product terms are coming to the multiplexers. So based on the requirement, either these product terms are being shared with the other macro cells or they are used in the same macro cell. So if they are used in the same macro cell, then all the product terms will go to the OR gate. And if more product terms are required by this macro cell, then they can accept it from the upper and the lower macro cell. But on the other hand, if these product terms are not required in the current macro cell, then some or all the product terms can be combined together and they can be shared with the other macro cells. So once again, these 5 product terms can be combined with the other product terms that is received from the upper and the lower macro cell. And once again, it can be shared with the other macro cells. So in this way, with the help of the product term allocator, these product terms can be shared with the other macro cells. Now apart from being part of the output function, these product terms can also be used as a control inputs in the macro cell. For example, by applying either 1 or 0 as one of the input to this XOR gate, it is possible to invert the output of this OR gate. But here, it can also be inverted based on the output of the product term. That means here, this one of the product term can decide when this output will get inverted. So similarly, instead of the global set and the global resets for the flip-flop, one can also use the product term set and the product term reset. And likewise, the output tri-state buffer can also be enabled or disabled based on the product term output. And similarly, the clock signal to the flip-flop can be applied either through the global clock or through the product term clock. So in this way, these product terms can also be used as a control inputs to configure the various functions in the macrocell. Now in each macrocell of the CPLD, both combinational output, that is the output of this XOR gate, and the registered output, that is the output of the flip-flop, will go to the multiplexer. And through the selection switch, it is possible to select whether we want the registered output or the combinational output. That means the output of this multiplexer is basically output of this macrocell. And as you can see, this output will go to the IO block as well as the switch matrix. So that is all regarding the macrocell of the CPLD. So now, let us see the function of this IO block. So as you can see, this IO block consists of the inputs and the output buffer. So this output buffer can be enabled either using the global output enables, or it can also be enabled using the product term output enable. Moreover, it can also be directly connected to the permanent 1 or the permanent 0. So all these inputs are going to the multiplexer, and through the selection switch, it is possible to select one of the inputs. So here, these global signals like the global output enable will be common to the all macrocells. But if you see this product term output enable, then it will be specific to the particular macrocell. So apart from that, this output buffer also has a provision to control the slew rate. So whenever this output buffer is off, then the output of the macrocell will not reach the output pin. And at that time, this pin can be used as an input. So through this input buffer, this applied input will reach the switch matrix. And from there, it can be accessed by the all macrocells. And in fact, the other logical array blocks can also access this specific input. So that is the input output block in the CPLD. So finally, now let us talk about the switch matrix. So like I said, some manufacturers also call it as the programmable interconnect array. So we have seen that through a switch matrix, it is possible to route the signal between the different logical array blocks. Moreover, through the input output block, all the inputs will come to the switch matrix, and through the switch matrix, it is possible to route these inputs to the different logical array blocks. That means through the switch matrix, all these different logical array blocks as well as the input output blocks are connected with each other. So all the switching configurations of the switch matrix as well as the other configurations in the macrocells are stored in the EPROM or the flash memory. So through the programming, all these configurations are stored either in the EPROM or the flash memory of the CPLD. So now whenever the CPLD is powered on next time, then based on these configurations, the signals will be routed between the different logical array blocks, and accordingly, we will get the desired output at the output pins. Now the advantage of the CPLD is that all the signals are routed through this switch matrix. So because of that, the overall delay in the circuit is predictable. But the issue is that if you want to scale up the system, then it is the challenging, because as you can see, as the number of logical array block increases, then the number of inputs that is coming to the switch matrix as well as the number of outputs that is going away from the switch matrix will also increase. And because of that, the switch matrix will get bigger and bigger. So beyond one point, the scaling of the CPLD is impractical. Moreover, in the CPLD, the number of flip-flops or number of memory elements are limited. That means with the help of the CPLD, we cannot implement applications which requires very large memories. So they are suitable for the applications which requires more combination logic and does not require more memory elements. So basically, these CPLDs are used for designing the small control circuits for the instrumentation as well as the power electronics. Moreover, they can also be used for designing the optical encoders as well as the finite state machines. But these CPLDs cannot be used in the memory intensive applications. So in the applications which require more memory and requires more processing, the FPGA are the more suitable options. So in the upcoming videos, we will learn briefly about this FPGA. But I hope in this video, you understood what is CPLD and what is the internal structure of this CPLD. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.